Okay. In the last lecture, we have started with wave optics. In that, we have discussed different phenomena such as reflection, refraction, interference, diffraction, right? Then we have discussed about resolving power of telescope, right? In this lecture, we are going to continue with the same that electromagnetic wave is nothing but where electric and magnetic field occurs simultaneously. Therefore, they attain their maximum and minima at the same place and at the same time. Okay, the direction of electric and magnetic fields are mutually perpendicular to each other and as well as to the direction of propagation of wave. The speed of electromagnetic wave depends entirely on electric and magnetic properties of the medium in which the wave travels and not on the amplitude of their vibrations. Okay, next one. In the last lecture, we have talked about interference. What is interference? Interference is simply light plus light is either maximum of intensity or minimum of intensity. And as per that, we have obtained the two conditions. That is, first one is condition for constructive interference and condition for destructive interference, right? We have talked about that phenomena. Okay, let us revise the things. Okay, this part we have finished. Heisenberg's second dream, the blood principle, this point we have covered. Then after that, 8 minutes. Let me share a few things. Okay, so in the last lecture, we have talked about all these things, that is interference. 8 minutes. Okay, so where it is. This part you finished. Let me check. Okay. So interference of waves. What we say, interference is the phenomena where superposition of two waves takes place, due to which we will get alternate dark and bright bands. Okay. Here is first wave. That first wave is overlapping with another wave, right? So it follows constructive interference. What about the intensity? As per the superposition of theorem, that is total E equals to E1 plus E2. And for destructive interference, E equals to E1 minus E2. Here, we are assuming that E1 and E2 be the superimposing waves having intensity E1 and E2 respectively. Okay. So, as per the conditions, in order to observe the phenomena of interference, we should follow 4 conditions. That is, first one, sources should be narrow, sources should be monochromatic, sources should be of equal intensity, and sources must be coherent. These are the 4 conditions required to observe interference of waves. Okay. So this is the phenomena. that is interference phenomena. Due to that, at the center we will be getting bright band, and surrounding to bright band we are getting dark band on either side. After that, again bright band, again dark band. That means alternate dark and bright bands are observed due to interference of waves. The next one, if crest of one wave, if crest of one wave overlaps with crest of another wave, if crest of one wave overlaps with crest of another wave, and so on, then we are getting condition for bright band. And if crest of one wave overlaps with trough of another wave, then we'll be getting dark band. Okay, so this is called interference phenomena, right? The phenomena of the phenomena of one wave interfering with another and resulting redistribution of energy in space around the two sources of disturbance is called interference of waves. I told you the very simple definition for interference of waves, that is light plus light is either maximum of intensity where it follows condition for constructive interference. Okay, and light plus light equals to minimum of intensity where it follows destructive interference, and due to which respectively we can obtain condition for dark band and bright band. So this is all about interference of waves. Then few formulas. Okay. So from the point of view of examination, we have to remember that E equals to E1 plus E2, that is resultant intensity due to superposition of two waves respectively having intensity E1 and E2 is given by E equals to E1 plus E2. Similarly, similarly, uh, Similarly, applying superposition principle, the magnitude of resultant displacement of the waves due to the minima of intensity, okay, is given by E equals to E1 minus E2. Then next one, condition for constructive interference of waves. For constructive interference, I should be maximum, just we said that E equals to E1 plus E2. For constructive interference, I should be maximum, which is possible if cos phi equals to plus 1. Okay? Then, what is the phasor difference? Phasor difference is 2 n pi. Okay? Phasor difference is 2 n pi. N equals to 1, n equals to 2, n equals to 3. We are getting different types of spectra. And the corresponding path difference is delta equals to lambda upon 2 pi into 2 n pi. Because we know that if this is a wave, okay, if, yeah, if this is wave, okay, so it is having different characteristics such as time period, then phase difference, phase, crest, trough, difference in between crest and trough is of pi radians, and the total distance is lambda. Okay, and that means if one oscillation is completed by a wave, then corresponding phasor difference is here is 0 and here is 2 pi. That means when one oscillation is completed, how much is the phase phase associated with that wave corresponds to 2 pi. ठीक है? If 2 pi is the phase difference, then it corresponds to how much distance? That is lambda. What is lambda? Lambda is the path difference. What is 2 pi? That is the phase difference. Okay. And if this path difference, what is path difference? Path difference, that means difference in the path traveled by two waves. This is first wave, this one is second wave, and whatever is the path difference in between these two waves to reach at one particular point in order to have the superposition theorem, and if it follows certain conditions, then we can obtain the interference phenomena. So the path difference must be equals to n lambda. Path difference must be equals to n lambda. And due to constructive interference condition, I maximum at the maximum of intensity, that is constructive interference, is directly proportional to a plus b square. Right? Next one, for condition of destructive interference, we will get another condition that path difference is delta, and delta equals to lambda by 2 pi into 2n plus 1 into pi, and this is the path difference required to observe the interference phenomena. That path difference equals to n lambda for maximum of intensity, that is the condition for bright band. And in order to observe the destructive interference condition, this path difference must be equals to n plus or minus half into lambda. Okay, so these things you have to remember. Next, comparison of intensities of maxima and minima. We said that Imax is directly proportional to a plus b bracket square. I minima is directly proportional to a minus b bracket square. And I max upon I minimum, intensity corresponding to maximum of intensity equals to, upon intensity corresponding to each minimum of intensity is to be expressed in terms of a plus b bracket square upon a minus b bracket square. And this is solved using some rearrangement. Okay. So we are getting the condition I maximum upon I minimum equals to r plus 1 square upon r minus 1 square. Next one, few formulas we will remember about Young's double slit experiment. You have studied this Young's double slit experiment, right? And based on that, we have seen the interference pattern. Here, two coherent waves are to be obtained. There are two methods by which coherent sources can be obtained. The first one, that is division of wavefront. What is division of wavefront? That means this is the parent source. Here is parent source, and this parent source emits some secondary wavelets, and if these secondary wavelets are passing through such single slit, here is single slit, here is single slit, that means if original wave is passing through two slits as shown in figure, then we can obtain this is first wave and this is second wave, which is identical by all sense in terms of frequency, in terms of amplitude, in terms of intensity, similar to the characteristic features of this original source. म्हणजे ओरिजिनल सोर्सच्या ज्या कॅरेक्टरिस्टिक फीचर्स असतात त्याच कॅरेक्टरिस्टिक फीचर्स आपल्याला जेव्हा ही वेव्ह आणि ही वेव्ह जेव्हा प्रोपगेट होते आणि ह्या ठिकाणी सुपरइम्पोज होते, ठीक आहे, तर ह्या ठिकाणी आपल्याला मॅक्सिमम मिळेल की मिनिमम मिळेल. म्हणजे हा ओरिजिनल सोर्स आहे आणि ओरिजिनल वेव्स आहेत. Those original waves are to pass through two single slits to obtain coherent waves. Okay? Coherence means what? The two waves must have the phase difference either constant or 0. Those two waves are supposed to be coherent waves. Here, current source is one and same, and from that, again, we are getting two secondary waves as per Heisenberg's wave theory. This is first secondary source, this one is second source of wave. These two sources are coherent, and here we can obtain the either maximum of intensity or minimum of intensity. Depends on path reference. Here, the path followed by this first ray and path followed by this second ray, they are not identical. Some difference is there, right? Some difference in the path. Path means the distance traveled by first ray and distance traveled by second ray at the location of superposition. Difference in their path is observed. Okay, so depends on path difference, we may obtain the condition for maximum of intensity or minimum of intensity. Now let us assume that B is okay. This D is the capital D distance in between these slits, and here is screen, here is source, then slits, and here is screen where we are going to observe such interference pattern. Okay? So we are trying to calculate the path difference. Path difference is this distance is larger as compared to this distance. Therefore, S2P minus S1P. And if you are solving this, then we are getting final expression that path difference. This already you have studied all the expressions and everything. We are simply trying to revise the things. Okay? So path difference is coming as y into d upon d. What is d? This is the distance in between slits and screen. Y, that the distance from the central maxima to the P location. Distance OP. OP is what? The displacement of a wave, you may call. ठीक आहे. So ह्या ठिकाणी जर त्यांचं इंटरफिरन्स झालंच नसतं तर काय झालं असतं, हे सरळ येऊन ते त्यांचा मॅक्सिमा और मिनिमाने प्रोड्यूस केला असता, पण इथे इंटरफिरन्स होतं आणि म्हणून इथे आपल्याला मॅक्सिमा सापडतोय, मिनिमा सापडतोय. हा कशावरती डिपेंडंट राहतो, तर डेल्टा इक्वल्स टू वाय इंटू डी. वाय इज व्हॉट? द डिस्टन्स फ्रॉम सेंट्रल point to the first location. So delta equals to yt upon d. What is d? D is the distance in between two slits. Okay. Okay. So for n equals to 0, what we are getting? For y n equals to 0, if we are substituting n equals to 0, then obviously delta or y is also equals to 0. Y is what? Y is, you may call, the distance in between central point to either first maxima for n equals to 0, for second maxima for n equals to 1, and so on. So for n equals to 1, you will get this y1 equals to d lambda upon d. Okay. Then position of dark fringes. What is the condition? Condition we said that if path difference equals to n lambda, we'll get condition for bright fringes. If n equals to, path difference equals to, what we said? Path difference delta equals to n plus or minus half into lambda, right? So if you are solving this, then the condition will change as 2n plus 1 or minus 1 into lambda. Okay, upon 2 is there. So this is the condition, that is delta equals to 2n plus or minus 1 plus or minus 1 into lambda by 2. Plus or minus, if your n starts from, if n starts from 0, 1, 2 and so on, if n starts from 0, 1, 2, and so on to observe first order spectra, second order spectra, third order spectra, then we should take this condition. If your n starts from 1 to n minus 1 into lambda by 2. If we are discussing this is the condition for dark fringes, ह्याच्यासाठी आपण ही कंडिशन प्लस और मायनस येते म्हणून इथे आपण मायनस घेतला तर असं लक्षात येतं की इथे n ची व्हॅल्यू वी शुड स्टार्ट फ्रॉम 1, 2, 3 and so on. Okay, and as for that we can say that if we are substituting n equals to 0, then we will be getting condition for first minimum of intensity. And if you are substituting n equals to 1, then we are getting the condition of minimum of intensity for first order spectra. Okay, so like this we are just comparing the equations and we are getting different order spectra. For first order spectra, your y is what? Y is the distance in between central point O to the first maxima. For n equals to 0, for first minima, n equals to 1 for second order minimum of intensity, that is 3t upon that. This is the expression for fringe width. Expression for fringe width. What is fringe width? Fringe width is simply distance in between two successive fringes. म्हणजे इंटरफेरन्स पॅटर्न समजा असा असेल तर सेंटरला इथे ओ पोझिशन आणि इथे पी पॉइंट आणि इथे पण पी अँड पी डॅश. ठीक आहे, तर ह्या ठिकाणी जर मिनिमम ऑफ इंटेन्सिटी असेल आणि या पण ठिकाणी जर मिनिमम ऑफ इंटेन्सिटी असेल तर आपण असं म्हणू शकतो डिस्टन्स इन बिटवीन टू सक्सेसिव्ह maximums or minimums is called fringe width. Distance in between two successive dark bands, that is called dark fringe width. Distance in between two successive bright fringe is called bright fringe width, and so on. Okay, so these are the conditions. Ultimately, expression for okay, ultimately you will observe here that expression for bright fringe. आता इथे तीन वर्ड्स हे अल्टरनेटली मी यूज करू शकते. कंडिशन फॉर कंस्ट्रक्टिव्ह इंटरफेरन्स, कंडिशन फॉर maximum of intensity, or condition for bright band. It is one and the same. Similarly, I may use here the words like destructive interference, minimum of intensity, and condition for dark band. Okay, dark band, destructive, and minimum of intensity. Bright band, maximum of intensity, and constructive interference. म्हणजे एक्झाम्पलमध्ये ज्या वेळेला तुम्हाला असे वर्ड्स येत आहेत की कन्स्ट्रक्टिव्ह, ब्राईट बँड अँड मॅक्सिमम ऑफ इंटेन्सिटी, त्या ठिकाणी लक्षात ठेवायचे की आपल्याला कन्स्ट्रक्टिव्हचीच कंडिशन आपल्याला रेफर करायची. ओके, सो अल्टिमेटली यू आर ऑब्झर्विंग दॅट whether it is distance in between two successive bright fringes or two successive dark fringes, then also the fringe width is same. Okay, that is d lambda upon d. Okay, this expression for fringe width shows that if the fringes are equally spaced on the screen. Next, these expressions also you should remember distribution of intensity. Suppose the two interfering waves have same amplitude, say A, ठीक है, म्हणजे ज्या दोन वेव्स एकमेकाला सुपरइम्पोज करतात त्या वेव्हची अँप्लिट्यूड सेम आहे, कारण का त्यांची इंटेन्सिटी सेम आहे असं आपण म्हणतोय, तरच आपल्याला इंटरफिअरन्स पॅटर्न दिसतोय. ठीक आहे. सपोज द टू इंटरफिअरिंग वेव्स हॅव सेम अँप्लिट्यूड, से ए, देन हॅलो 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 सर, हॅलो हॅलो सर,
हा बोला.
कंटिन्यू असतात ना, येत आहेत ना?
हा, मी घरी आलो मॅडम, अमृत सर बसलाय.
ओके, ठीक आहे,
हा, त्याला फोन कर.
चालेल. Okay, suppose the two interfering waves have same amplitude, then I max is directly proportional to A plus A bracket square. That means intensity is going to be 4 times A square, right? Because A square plus 2A square, that is 4A square. म्हणजे इंटेन्सिटी जी आहे ती 4 टाइम्स इंटेन्सिटी ऑफ ओरिजिनल म्हणजे सुपरइम्पोजिंग वेव्स. सुपरइम्पोजिंग वेव्हची अँप्लिट्यूड जर ए इतकी असेल तर मॅक्सिमाच्या ठिकाणी जी इंटेन्सिटी मिळते ती 4 टाइम्स ए स्क्वेअर इतकी मिळते. यू मे इमॅजिन. So all the bright fringes have the same intensity. Next, and I minimum equals to 0. All the dark fringes have 0 intensity. Now, these conditions also we have talked about. Next one, why the color sync influence is observed. This is the application of interference. You might have observed in rainy seasons. In rainy seasons, when oil is spreaded on wet road. आपण बघतो की पावसाळ्यामध्ये पेट्रोलचं टँक थोडं थोडं पेट्रोलचं लिकेज झालं असेल तर रस्त्यावरती आपल्याला काही ठिकाणी ऑइल स्प्रेड झालेलं दिसतं. तर ती पर्टिक्युलर केस जर आपण व्हाईट लाईट सोर्सच्या प्रेझेन्समध्ये बघितलं तर आपल्याला असं दिसतं की कलर्सचे आपल्याला different colors are to be observed. Okay? What I am talking about, when the oil is spreaded on wet road, oil is spreaded on wet road, then that case is illuminated, that case is exposed with white light source, then what happens? You can see the colors. Just now we said that if path difference is either integral multiple of lambda, then we will be getting the condition for maximum of intensity. Okay? Here is the complementary condition. 2 mu t cos r equals to n lambda is the condition for dark band, and this is the condition for bright band. Okay? So all this is about the interference phenomenon. What you remember? You remember the different conditions. I max, I minimum, I max is directly proportional to 4a square, I max upon I minimum, and all that. Now let us discuss about diffraction condition. Okay, what is diffraction? Diffraction is simply the phenomena of bending of light beam around the corners and the encroachment of light within the geometrical shadow of the opaque obstacles is called diffraction. Let me simplify this relation that diffraction is simply bending of a light beam around the obstacle. ओके, ऑब्स्टॅकलच्या सभोवती आपल्याला जॉमेट्रिकल पॅटर्न्स ऑब्झर्व होणं अल्टरनेटली. ठीक आहे, मॅक्सिमा किंवा मिनिमा, तर त्याला आपण म्हणतो डिफ्रॅक्शन. डिफ्रॅक्शन इज व्हॉट? डिफ्रॅक्शन इज, लेट मी क्लॅरिफाय द थिंग्स. ओके, so suppose suppose here is source of waves, and it emits spherical reference like this. And if we know that light travels in a straight line path, but if any obstacle is coming in its path, if this is the object, if any obstacle of diameter d, if any obstacle of diameter d is coming in its path, then light is simply bending at the surface. Over the surface, it bends like this. Okay? So, like this. Spreading of a light beam around the obstacle. Same is the case. This beam of light is going to be spreaded in all possible direction. It spreads over the surface. Okay, so like this. So the light is simply bending around the obstacle. आता ज्या ठिकाणी लाईटच नाहीये तर तिथे काय होणार? तिथे त्यांचं डिफ्रॅक्शन होणारच नाही, तर आपल्याला इथे कम्प्लीट शॅडो दिसणार, जॉमेट्रिकल शॅडो ऑफ द ऑब्जेक्ट. आणि ह्याच्या तिथपर्यंत आपलं रे ऑफ लाईट एंटर होत नाही, त्यामुळे तिथपर्यंत आपल्याला या ऑब्जेक्टची जॉमेट्रिकल शॅडो दिसणार, कारण तिथे लाईटच नाहीये. पण जे बेंड झालेले बीम असतात ते काय प्रोड्यूस करतात? तर अल्टरनेटली डार्क अँड ब्राईट बँड्स around to the geometry of light around the corners and the encroachment of light within the geometry इथे इन्सिडेंट होते, त्यावेळेला ती सरळकडे जाऊ शकत नाही, म्हणून ती थोडी फोटॉन्स असतात. वेव्ह इज सिम्पली अ स्ट्रीम ऑफ फोटॉन्स, म्हणजे एकच वेव्ह नसते, अ स्ट्रीम ऑफ फोटॉन्स. त्यामुळे एक फोटॉन इथे इन्सिडेंट झाला, एक इथे इन्सिडेंट झाला, इथे इन्सिडेंट झाला, की अशा डिफरंट वेव्स ज्या असतात त्या पुढे प्रोपगेट होतात. ठीक आहे, आता इथून डिफ्रॅक्ट झालेली वेव्ह इथे सुद्धा इन्सिडेंट इथे सुद्धा येऊ शकते. इन ऑल पॉसिबल डायरेक्शन्स इट विल प्रोपगेट, and there is a possibility that they may interfere with each other. Okay, so what we said, that bending of a light beam around the obstacle, that is first case. मग आता परत आपण एक दुसरा पार्ट विचारात घेऊया. इथे समजा सोर्स आहे आणि इथे स्लिट आहे, ही अशी स्लिट आहे, स्लिट ऑफ स्लिट विड्थ ए म्हणूया आपण, म्हणजे ही स्लिट विड्थ आहे, हे डिस्टन्स. ठीक आहे, हे डिस्टन्स डी असेल किंवा ए असेल, डिपेंड्स ऑन द नोटेशन्स इन डिफरंट बुक्स. सो लेट अस सपोज दॅट ए इज द स्लिट विड्थ. मग इथे काय होतं, ते हे शार्प एजेस असतात. दीज आर टू शार्प एजेस, फर्स्ट वन, सेकंड वन. आता इथून लाईट सरळ पुढे ट्रॅव्हल होते. जस्ट ट्राय टू अंडरस्टँड. एक एक कन्सिडरेशन आपण घेतलं की लाईट वेव्ह जर ऑब्स्टॅकलच्या ऑब्स्टॅकलवरती इन्सिडेंट झाले तर आपल्याला बेंडिंग ऑफ अ लाईट बीम ऑब्झर्व होते. आता इथे दुसरं कन्सिडरेशन आहे. इफ द सोर्स ऑफ वेव्स emitting large number of photons or large number of waves, they are simply traveling in a straight line path if not any single obstacle is coming in its path. ठीक आहे, म्हणजे ह्या वेव्स इथून सरळ अशा पुढे जाऊ शकतात. पण जेव्हा या वेव्स इथे येऊन इन्सिडेंट होतात, इथे येऊन इन्सिडेंट होतात त्यावेळेला हा पॉइंट आणि हा पॉइंट हा जो आहे, ही वेव्ह इथे इन्सिडेंट झाली, ही वेव्ह इथे इन्सिडेंट झाली. ठीक आहे, आणि ह्या दोन वेव्स आता सरळ पुढे न जाता त्या काय होतात, इथून अशा डिफ्रॅक्ट होतात. डिफ्रॅक्ट म्हणजे स्कॅटर्ड होतात. ठीक आहे, इथे आलेली वेव्ह इथून सुद्धा डिफ्रॅक्ट होते अशी अशी. ठीक आहे, अँड देर इज अ पॉसिबिलिटी दॅट ॲट वन पर्टिक्युलर पॉइंट they may superimpose on each other to produce maximum of intensity or minimum of intensity. Getting my point? If this is source of waves, those waves which are not suffered by any point, any obstacle, can simply travel in a straight line path. But when these waves are interacting at the edges, they are getting scattered, they are getting bent. Okay, म्हणजे इथली वेव्ह इकडे बेंड होऊ शकते, इथली वेव्ह इकडे बेंड होऊ शकते, इथली वेव्ह इकडे बेंड होऊ शकते. ठीक आहे, देर इज अ large possibility of the scattering of light waves, and on the screen we will get either maximum of intensity or minimum of intensity. So this is the point of central maxima, की ज्या ठिकाणी ह्या सर्व वेव्स ज्या बेंड होत नाहीत, ज्या वेव्स बेंड होत नाहीत त्या काय करतात, इथे इल्युमिनेशन कंप्लीट रिजन मध्ये देऊ शकतात. ठीक आहे, दिस इज द कंडिशन फॉर दिस इज द रिजन वेअर all the waves which are simply traveling in a straight line path are to be illuminated. ठीक है, are to be used to produce central maximum of intensity. म्हणजे फर्स्ट एस्पेक्ट असं आहे की लाईट रेच्या पाथ मध्ये एखादं ऑब्स्टॅकल आलं तर आपल्याला डिफ्रॅक्शन ऑब्झर्व होतो. दॅट इज फर्स्ट केस. सेकंड केस मध्ये जर रे ऑफ लाईट या आपण एखाद्या स्लिट मधून पास केल्या तर ॲट द एजेस ऑफ द स्लिट्स दे आर गोइंग टू बेंड, अँड these bending waves are likely to superimpose on each other to produce interference effect, that is to produce maximum of intensity or minimum of intensity, right? So that aspect is called the diffraction of light. You can simply see here, this is source of waves, here is slit with E, A or D, any notation you may use. So in your book, this is the notation given for the slit width. ठीक आहे, सो सी here, ज्या वेळेस इथे बेंड झालेले नसतात त्या अशा सरळ पुढे जातात आणि इथे आपल्याला मॅक्सिमम ऑफ इंटेन्सिटी मिळते बाय फॉलोइंग आयस डायरेक्टली प्रोपोर्शनल टू 4a². पण ज्या वेव्स इथे बेंड होत आहेत, इथे बेंड होत आहेत, त्या इथे आता मॅक्सिमम प्रोड्यूस करतात किंवा मिनिमम प्रोड्यूस करतात, डिपेंड्स ऑन path difference of these two propagated waves. Okay. So this is called diffractionate single slit. Now next one. Yeah, this is the region of geometrical shadow. If the obstacle is coming, if this is slit width, this is the brighter portion which is called central maximum, right? So this is geometrical shadow. On either side of geometrical shadow, you will get maximum of intensity or minimum of intensity. This is called diffraction at an obstacle, diffraction at a slit. Now, at an angle of diffraction theta equals to 0. Okay, there are two types of diffractions. First one, Fresnel's class of diffraction. Second one, Fraunhofer's class of diffraction. What is the difference? That also we will see. At an angle of diffraction theta equals to 0. That means the rays which are not bent, ज्या waves bent झालेल्या नसतात त्यांचा अँगल ऑफ डिफ्रॅक्शन हा थीटा इक्वल्स टू 0 असतो. त्या सरळ पुढे ट्रॅव्हल करतात. They are simply traveling and going to focus to produce the central maximum of intensity. Okay, here theta equals to 0 produces bright region. ठीक है? So this is the Fraunhofer's diffraction. What is the difference between Fresnel's class of diffraction and Fraunhofer's class of diffraction? Let us remind things. In Fresnel's class of diffraction, either spherical or cylindrical wavefront is to be used. Second difference, no lens system is used, right? And distance in between source to the screen and screen to the obstacle, distance in between source the distance in between source to the obstacle and obstacle to the screen, the distance in between source to the screen and distance in between source to obstacle. म्हणजे इथे कुठे तुमचं सोर्स असणार, इथे source to the obstacle, which is this obstacle. This is the slit width, right? Slit width is the obstacle we are assuming. So this is the distance in between source to the slit or source to the obstacle and obstacle to the screen. Obstacle to the screen is finite. In case of Fresnel's class of diffraction. In Fraunhofer's class of diffraction, what is the difference? Here, distance in between source to the obstacle or source to the slit is infinite. At the same time, distance from obstacle to the screen is infinite. Let us revise the thing. There are two classes of diffraction. That is Fresnel's class of diffraction and second Fraunhofer's class of diffraction. Fraunhofer. The first difference, no lens system is required. No lens system. Second difference, distance in between source to obstacle or screen. Source to obstacle and slit. Obstacle or slit. Okay. Distance in between source to obstacle or source to slit is finite. And third difference, see, that is which wavefront, cylindrical wavefront or spherical wavefronts are to be used. Okay, and what is comparison for Fraunhofer's diffraction? Lens system is used. Second difference, source to the obstacle or slit is source to the obstacle or slit to the screen. Source to the distance in between source to obstacle and obstacle to the screen is infinite for Fraunhofer's class of diffraction. And third difference, instead of cylindrical or spherical wavefront, we are using plane wavefront. Okay, plane wavefront. So this is the plane wavefront. How to obtain the plane wavefront from spherical wavefront? If this is a source, right, and source emits at the cylindrical or spherical wavefront, and if it is allowed to pass through convex lens, म्हणजे हा स्फेरिकल वेव्हफ्रंट जर एखाद्या कॉन्व्हेक्स लेन्स मधून आपण पास केला तर इथे आपल्याला प्लेन वेव्हफ्रंट जनरेट होतो. ठीक है. So this is every point on this wavefront will act as a source of secondary waves. ठीक है. So this is the plane wavefront. This one. This is called plane wavefront. How to obtain that? Here is source. Source emits either cylindrical wavefront or spherical wavefront. All these concepts I have explained in the previous lecture. ठीक है. So this secondary waves, sorry, the cylindrical waves or spherical waves are to be passed through a convex lens. Then we can obtain such plane wavefront where all the points on this wavefront will act as a source of secondary waves, and those secondary waves are simply propagating through a convex lens to get focused at point O when theta equals to 0. Okay? When theta equals to 0. Next. Yeah, the wavelet from single wavefront reach the center O on the screen in same phase and hence interfere constructively to give central or principal maxima or primary maxima. Now, second condition. Second condition. This is the Fraunhofer's diffraction where plane wavefront is to be used. Okay, and this plane wavefront will act as the large number of waves, and if this convex lens is placed, then here you may observe if this plane wavefront is simply passing by arranging the lens system is like this, then obviously it is going to be diffracted. Okay, जर इथे लेन्स सिस्टीम नसती तर ह्या वेव्स ज्या आहेत त्या सरळ पुढे गेल्या असत्या आणि इथे फोकस झाल्या असत्या. ओके, पण इथे काय होतं की ह्या एजला आणि या एजला लाईट ही काय होते, बेंट होते, आणि ही बेंट झालेली वेव्ह जेव्हा या कॉन्व्हेक्स लेन्स मधून आपण पास करतो त्यावेळेला हा जो अँगल असतो ह्याला म्हणतात अँगल ऑफ डिफ्रॅक्शन. ह्याला म्हणतात अँगल ऑफ डिफ्रॅक्शन. ठीक आहे, ह्याला म्हणतात अँगल ऑफ डिफ्रॅक्शन. ठीक आहे, this is also angle of diffraction, and when these diffracted waves are passing through this convex lens, then we are getting different points at which these waves are supposed to interfere. ठीक है, so this is central maxima P1. The slit is imagined to be divided into two parts that we said. Then what is the alternate condition we are getting for minimum of intensity? That is called condition for bright, condition for dark band. What is the condition for dark band? If E is slit width, E is slit width, स्लीटची विड्थ किती आहे, ई असेल किंवा ए असेल, then what is the condition to observe minimum of intensity is called E sin theta equals to n lambda. Here n equals to 1. Okay, if theta is very small, then sin theta equals to theta, and therefore the condition utilized is called theta equals to n lambda. Theta equals to n lambda upon E. ठीक है, if theta is very small, sin theta can be taken as theta equals to n lambda upon E. जर तुमची स्लीट विड्थ डी इतकी असेल तर हाच फॉर्म्युला कसा होतो, तर n lambda upon D. Therefore D equals to काय असणार, n lambda upon theta, like that. ठीक है, so this is called the condition for minimum of intensity. Second is the case that is at angle of diffraction theta equals to theta 2. If n equals to 1, theta equals to theta 1, where we can obtain P1. P1 is the, what is P1? P1 is the location of first minimum of intensity. And what is P2? P2 is n equals to 2. Here n equals to 1. Okay, so the slit is imagined to be divided into 4 equal parts, and we are going to calculate path difference, right? So as per that, let us check. So for n equals to 1, dark band. For n equals to 2, again dark band corresponding to P1 and P2. Okay. Okay. This pattern observed is called intensity distribution. Intensity distribution curve due to the phenomena of diffraction. Which diffraction? Fraunhofer's diffraction. So at the center we are getting central maximum of intensity, and surrounding to this central maximum of intensity we are getting alternately first minima, second minima, and so on. This is central maxima. This is first secondary maxima. Okay, first secondary maxima. This also first secondary maxima. Like that. Okay. Okay. So for nth secondary maxima, the slit can be divided into n equal parts. What is the condition? Just now we said d sin theta equals to n lambda. D sin theta equals to n lambda. If n equals to 1, theta equals to theta 1. If n equals to 2, theta equals to theta 2. N equals to 3, theta equals to theta 3, and so on. Okay? Alternately, we are getting the condition for secondary minimum of intensity. We are getting odd integral multiple. By following the condition, instead of n lambda, we will use the condition n plus or minus half into lambda, and we are getting the conditions as d sine theta equals to 3 lambda upon 2, 5 lambda upon 2, and so on. Okay. So this is all about the diffraction phenomena. You have to remember this expression. Now, we will start with the examples based on all the explanation given. Let us focus on which type of the examples are likely to be asked. हे सगळं थिअरी समजणं सोपं आहे, पण थिअरी अप्लाय करायची आणि आपल्याला एक्झाम्पल सॉल्व करायचे. Okay. Let us take example. In a diffraction experiment from a single slit, okay, in diffraction experiment from a single slit, the angular width of central maxima does not depends upon, ठीक है, म्हणजे angular width in terms of theta we may define, ठीक है, angular width of the central maxima does not depends on ratio of wavelength and slit width. Slit width is d, wavelength is lambda. What the expression we are having? We are having the expression that d sin theta equals to n lambda. Okay. So here theta equals to n lambda upon d, because if theta is very small, sin theta is to be considered as theta, and this is the angular width depends on theta value, because on the screen we are getting central point as O, and this is the first point, and this distance is y, that is angular width, and this angular width depends on angle of diffraction. Okay, so let us revise the things. Okay, so ratio of wavelength and slit width. distance of the slit from the screen, the length of light used, and width of the slit. म्हणजे diffraction experiment मध्ये angular width of central maxima does not depends upon. आता फॉर्म्युला जर तुम्ही बघितला तर इथे लक्षात येते. In diffraction experiment from a single slit, the angular width of central maxima, if we are substituting n equals to 2, then we are getting theta equals to 2 lambda upon a, because if we are saying a is the slit width, काही बुक्स मध्ये डी वापरतात, काही बुक्स मध्ये ए वापरतात. ठीक आहे. So in diffraction experiment from a single slit, the angular width of central maxima is theta equals to lambda by a for first order. Second order, 2 lambda by a, and so on, where lambda is the wavelength of light used and a is the width of the slit. So angular width does not depends upon the distance of the slit from the screen. Upon the distance of the slit from the screen. Actually, distance इथे सोर्स आहे, इथे स्लिट विड्थ आहे आणि इथे स्क्रीन आहे, आणि हे जे डिस्टन्स आहे त्याला आपण काय म्हणतो तर डी असं म्हणतो. ठीक आहे. सो अँग्युलर विड्थ डज नॉट डिपेंड्स अपॉन द डिस्टन्स ऑफ द स्लिट फ्रॉम द स्क्रीन. ओके, सो दॅट इज युअर करेक्ट आन्सर. अँग्युलर विड्थ डज नॉट डिपेंड्स ऑन distance of the slit from the screen. That means B answer is correct. Okay. Now, next one. In Young's double slit experiment, green light is incident on 2 slits. Okay. Young's double slit मध्ये monochromatic source वापरला तुम्ही आणि त्याची लाईट ग्रीन आहे. The interference pattern is observed on a screen. Which of the following changes would cause the observed fringes to be more closely spaced? प्रश्न लक्षात घ्या. जर आपण इथे ग्रीन लाईट वापरली आहे, यंग्स डबल स्लिट एक्सपेरिमेंट मध्ये मोनोक्रोमॅटिक सोर्स ऑफ लाईट म्हणजे ग्रीन कलर, आणि ग्रीन कलरची वेवलेंथ जी असते, वेवलेंथ फॉर ग्रीन कलर इज अप्रॉक्सिमेटली 5500 Armstrong unit. Okay, the interference pattern is observed. हा वेवलेंथ इन्सिडेंट करून आपल्याला इंटरफिरन्स पॅटर्न दिसला. ठीक आहे. आता ते म्हणतात की which one of the following changes would cause the observed fringes to be more closely spaced. म्हणजे फ्रिंज विड्थ ही खूप कमी असली पाहिजे, किंवा तर कोणत्या केसमध्ये. हा स्टँडर्ड तुमचा इंटरफिरन्स पॅटर्न, हा स्टँडर्ड इंटरफिरन्स पॅटर्न, आणि या स्टँडर्ड इंटरफिरन्स पॅटर्न मध्ये ह्या जे दोन डार्क बँड किंवा ब्राईट बँड दिसतात जवळजवळ, त्यांच्यातलं स्पेसिंग हे आपल्याला कमी झालं पाहिजे ॲज कम्पेअर्ड टू हे स्टँडर्ड इंटरफिरन्स पॅटर्न. ओके, हे डिस्टन्स कमी झालं पाहिजे ॲज कम्पेअर्ड टू दिस डिस्टन्स इन बिटवीन 2 सक्सेसिव्ह डार्क बँड्स और ब्राईट बँड्स. These should be closely spaced. आता इथे ऑप्शन दिले, मूविंग द स्क्रीन अवे फ्रॉम द स्लिट्स, डिस्टन्स चेंज केलं तर इंटरफिरन्स पॅटर्न हा त्यांच्यामध्ये फ्रिंज विड्थ जी आहे ती कमी होईल का, हा पहिला प्रश्न. युजिंग ब्लू लाईट, आता ब्लू लाईटची मूविंग द स्क्रीन अवे फ्रॉम द स्लिट म्हणजे डी, पहिला ऑप्शन सांगतो इफ डी इज व्हॅलिड, डी व्हॅलिड केला. ओके, डी व्हॅरी केला. सेकंड डिफरन्स, युजिंग ब्लू लाईट इन्स्टेड ऑफ ग्रीन लाईट. आता ब्लू कलरची वेवलेंथ जी असते लॅम्बडा बी इक्वल्स टू समथिंग 4800 सपोज. ठीक आहे. सो इट इज लेस ॲज कम्पेअर्ड टू ग्रीन लाईट. लॅम्बडा फॉर ब्लू कलर 4800 Armstrong, something 5300 4800 Armstrong unit. Then using red color instead of green light, म्हणजे ग्रीन लाईटच्या ऐवजी जर आपण पुढची लाईट वापरली तर रेड लाईट वापरली, तर रेड लाईटची वेवलेंथ काय असते तर 6500 Armstrong unit. ठीक आहे. And fourth option, reducing the separation between 2 slits. Okay, separation in between 2 slits हे जर आपण A चेंज केला separation in between two slits. Fourth option कोणता? हा एक पहिला ऑप्शन डी व्हॅरी, सेकंड फोर्थ ऑप्शन ए व्हॅरीज, ए व्हॅरी केला. थर्ड ऑप्शन सॉरी हा फर्स्ट हा फोर्थ हा सेकंड आणि हा थर्ड. तर याच्यापैकी कुठलीही कंडिशन इम्प्लिमेंट होऊ शकते. लेट अस फाइंड व्हॉट इज द डिस्टन्स बिटवीन फ्रिंजेस ऑफ द फ्रिंज विड्थ. ठीक आहे, म्हणजे असं ते विचारतात आपल्याला. 4 केसेस आहेत आपल्याकडे. What is the formula? Fringe width. This is the formula. We have seen this formula. That is distance in between two successive fringes, either for dark band or for bright band. It is same. What is the separation in between? Separation in between slit to the screen. Lambda wavelength. D is slit width. ठीक है, where lambda is wavelength of light, d is distance of slits from the screen, d is separation between the slits. So to reduce the space between fringes, what should be varied? D should be reduced. कारण इथे d आहे, हा सिंपल फॉर्म्युला जर लक्षात ठेवला तर इथे लक्षात येतं बीटा इक्वल्स टू लॅम्बडा इंटू डी अपॉन डी. ठीक आहे. So to reduce the space between fringes, D should be reduced, D should be increased, lambda should be reduced. Which one is correct? ठीक है. So to reduce the space between things, D should be reduced, D should be increased, lambda should be reduced. Okay. नाव ह्यातलं आपण एखाद्या सेटअप मध्ये काय चेंज करू शकतो? कारण हा सेटअप सेम आहे, म्हणजे डी आणि लॅम्बडा हे सेम आहे. सॉरी, हा डी आणि हा डी. दिस इज स्लिट विड्थ अँड दिस इज सेपरेशन इन बिटवीन स्लिट टू द स्क्रीन, हे सेम आहे. ठीक आहे. आणि आपल्याला इंटरफिरन्स पॅटर्न दिसलाय. तो इंटरफिरन्स पॅटर्न आपल्याला क्लोजली स्पेस पाहिजे असेल त्याच कंडिशन्स ना, तर हा डी आणि हा डी आपण चेंज करतोय आणि लॅम्बडा फक्त आपण जर व्हेरी केला. ब्ल्यू लाईट हा शॉर्टर वेवलेंथ. आता आपण बघितलं ब्ल्यू लाईट याची वेवलेंथ किती आहे? कमी आहे, 4800 एंगस्ट्रॉम युनिट ॲज कम्पेअर्ड टू रेड कलर और ग्रीन कलर. ग्रीन कलरचा हे स्टँडर्ड होता आणि ब्लू कलरची वेवलेंथ काय आहे तर कमी आहे. आणि ब्लू कलरची वेवलेंथ जर आपण यूज केली तर ऑटोमॅटिकली हे काय होऊ शकतं तर बीटा आपल्याला कमी होऊ शकतो. सो ॲज ब्लू लाईट हॅज शॉर्टर वेवलेंथ देन दॅट ऑफ ग्रीन लाईट. सो बाय युझिंग द लाईट इन्स्टेड ऑफ ग्रीन लाईट द फ्रिंजेस बिकम मोर क्लोजली. दॅट इज द ऑप्शन. ठीक आहे. सो मुव्हिंग द स्क्रीन अवे फ्रॉम द स्लिट्स using blue light. So this is the correct answer. Using the blue light instead of green light. That is the correct answer. ठीक आहे. हा डी त्या सेटअपसाठी सेम आहे, हा डी त्या सेटअपसाठी सेम आहे. मग व्हॅरी कोण करू शकतो आपण? लॅम्बडा करू शकतो, की जेणेकरून त्याच्यावरती बीटा आपण क्लोजली स्पेस्ड फॉर्म करू शकतो. ठीक आहे. नेक्स्ट थर्ड एक्झाम्पल. Try to understand the example first. The light of wavelength lambda. Okay, lambda is incident on or slit width. आता इथे notations given आपण म्हणूया. Lambda is incident on or slit width. किती आहे? D की slit width आहे. The resulting diffraction pattern is observed on a screen Okay, the resulting refraction pattern is observed on a slit at a distance of d. म्हणजे स्लिट आहे, स्लिट पासूनचं स्क्रीन पर्यंतचं डिस्टन्स, स्लिट पासून स्क्रीन पर्यंतचं डिस्टन्स हे किती आहे, डी इतकं आहे. ठीक आहे. इफ लिनियर विड्थ ऑफ प्रिन्सिपल मॅक्सिमा is equal to the width of the slit. Okay, equals to width of the slit. Then the distance d is given by, if linear width of the principal maxima is equal to width of the slit, म्हणजे width of the slit आपण किती म्हटलं तर d इतकं म्हटलंय slit width. Linear width is same as slit width. Okay, then the distance d, how to express, how to get this d? We know that linear width of the principal maxima is given by beta equals to 2d lambda upon d. What is d? D is the distance in between slit to the screen, lambda is wavelength, and d is what? Slit width. ठीक है. So linear width or fringe width we are calling. Linear width or fringe width of central maximum beta equals to 2d lambda upon d. It is given that linear width of the principal maxima is equal to width of the slit, and therefore if beta equals to d, beta equals to d, then what happens? We are substituting here beta equals to d, 2d lambda upon d. Therefore d equals to d square, d equals to d, we are keeping to one side, d coming here, d square upon 2 lambda, d square upon 2 lambda. So this is the correct answer. Okay, formula हा लक्षात ठेवला आहे की fringe width 2d lambda upon d. आता तुमच्या पुढे हा प्रश्न निर्माण होतोय की हा इथे आपला 2 आलाय, कारण का तर ही तुमची स्क्रीन आहे आणि इथे तुमचा P1 पॉइंट आहे, इथे तुमचा सेंट्रल मॅक्सिमम आणि इथे तुमचं काय आहे P1 डॅश आहे स्क्रीनवरती. ठीक आहे. आणि इथून इथंपर्यंतचं डिस्टन्स, इथून इथंपर्यंतचं डिस्टन्स. ओके, इथून P1 to P1 dash, that is called linear width or fringe width. Fringe width is distance in between two successive fringes. इथून इथपर्यंत किंवा इथून इथपर्यंत हे टोटल डिस्टन्स, आणि म्हणून इथे 2 येतो हे लक्षात घ्या. आणि फॉर्म्युलामध्ये पण हेच आहे, बीटा इक्वल्स टू 2d lambda upon d. It is given that so what is the correct option? D square upon 2 lambda. Next one, in a biprism experiment, you have studied this. So in biprism experiment, there are 2 cases you have studied where the coherent sources can be obtained with the help of division of wavefront, right? So in biprism experiment, the distance between source and eyepiece is 1.2 meter. Yes, distance between source and eyepiece is 1.2 meter. Means capital D equals to 1.2 meter. The distance between two virtual sources is 0.84 millimeter. Okay, that means two virtual sources, दोन waves च्या coherent waves आहेत. D equals to किती आहे 0.84 into 10⁻³ meter. Then the wavelength of light used, if eyepiece is to be moved transversely through a distance of 2.799. Okay, 2.799. Okay, to shift 30 fringes. बघा काय म्हटलंय, म्हणजे 30 fringes ऑब्टेन करण्यासाठी टेलिस्कोप किंवा आयपीस जो असतो तो किती डिस्टन्स मधून व्हेरी केला पाहिजे, तर 2.799 सेंटीमीटर मधून आपल्याला शिफ्ट करायचंय. ठीक आहे, सेंट्रल मॅक्सिमम असून इतकं डिस्टन्स आपण व्हेरी केलं तर आपल्याला 30 इंचेस क्रॉस होतात. म्हणजेच या ठिकाणी जर आपल्याला बीटा फाइंड करायचं असेल, व्हॉट इज बीटा? बीटा इज सिम्पली डिस्टन्स इन बिटवीन टू सक्सेसिव्ह फ्रिंजेस. ओके, बट इथे जे डिस्टन्स दिलंय ते किती आहे? 2.799 सेंटीमीटर. For how many coverage? That is coverage of 30 fringes. So we can calculate beta by simply having 2.799 into 10 raised to minus 2 upon kiti fringes? 30 fringes. So like that we'll be able to find beta value. In a bioprism experiment, wavelength of light used is given by lambda equals to d beta upon capital T. What is d? D is the separation between two virtual sources. What is beta? Beta is the fringe width. What is d? Distance in between screen to the slits, you may call. Distance in between slits to the screen. Then use the different interpretation. What is this d? D is simply the distance between source and the eyepiece. मी काय म्हणते, source and the slit, the distance is capital D, where beta is the fringe width, D is the distance between two sources, D is the distance between source and eyepiece. ठीक है, just now we have talked D equals to 1.2 meter, D equals to 0.84 millimeter. Yes, this is correct. Now substituting these values in equation 1, we get, what is the formula? Lambda equals to D into beta upon D. So if you are calculating this, then this is the correct answer. That is 6533 Armstrong unit. That is first one, first option is correct one. So you need to remember this formula. You need to understand for how much distance, how many fringes are observed. हे डिस्टन्स हे 30 फ्रिंजेस मधलं आहे. आपल्याला एका फ्रिंज मधलं, एका सक्सेसिव्ह फ्रिंजेस मधलं डिस्टन्स पाहिजे, म्हणून आपण त्यात तिथे 30 ने डिवाइड करतोय. ठीक आहे, नेक्स्ट वन. इन यंग्स डबल स्लिट एक्सपेरिमेंट, फिफ्थ डार्क फ्रिंज, विच डार्क फ्रिंज? राईट, फिफ्थ डार्क फ्रिंज म्हणजे n equals to 5 is formed opposite to one of the slit. Okay, if d is the distance between slits, this is the distance between slits and the screen, my total distance, screen पासूनचं स्लिट पर्यंतचं डिस्टन्स हे किती आहे? d. d equals to not given. Okay, that is not given, and d is the separation between the slits. Wait. D is the separation between two slits, means slit width. Okay, then the wavelength of the light used, या ठिकाणी आपल्याला लॅम्बडा फाइंड करायचं आहे. व्हॉट इज लॅम्बडा? डार्क फ्रिंजेस आहेत. ओके, डार्क फ्रिंजेस असल्यामुळे आपलं एक्सप्रेशन हे काय होतंय, तर n लॅम्बडाच्या ऐवजी आपण 2n-1 असं वापरतो. ओके, सो पोझिशन ऑफ n द डार्क फ्रिंजेस, हे डिफरन्स लक्षात घ्या. ब्राईट फ्रिंज असते तर ह्याच्याऐवजी आपण फक्त n लॅम्बडा वापरला असता, ह्याच्याऐवजी फक्त n लॅम्बडा. पण इथे डार्क फ्रिंजेस असल्यामुळे आपण काय वापरतोय? 2n-1 into lambda by 2. So the formula is position of nth dark fringe in Young's double slit experiment is given by xn equals to d upon d into 2n-1 into lambda by 2. So lambda corresponds to, from this equation we will be getting lambda equals to 2 into this 2 xn, this d is taken here, upon d into 2n-1. What is given? N is given. Fifth dark fringe is observed. Now, opposite to one of the slits, okay, फिफ्थ डार्क फ्रिंज ही कुठे ऑब्झर्व होतीये, तर एका स्लिटच्या समोर 2 of x5 इक्वल्स टू डी. म्हणजे x5 जितकं असेल त्याच्या 2 टाइम्स हे डिस्टन्स काय असणार, डिस्टन्स बिटवीन 2 स्लिट्स असणार. ओके. Okay, so put n equals to 5 in equation 1. What you will be getting? Lambda equals to 2x5 into d. कारण हे डिस्टन्स आपल्याला फिफ्थ डार्क बँडला पाहिजे. ओके. 2x5 into d upon d, it is there 2n minus 1, 2 into 5 minus 1 equals to x5 into d. x5 हे किती आहे, 2x5 equals to d आहे. 2x5 हे लक्षात आलं पाहिजे. हे लक्षात आलं तर लगेच आपण इथे फॉर्म्युला सबस्टिट्यूट करतो. d into d upon capital D into 10 minus 1. ठीक आहे. So what is the correct option? That is lambda equals to d square upon 9d. d into d, d square, 10 minus 1, 9 into d. So d square upon 90. So this is correct option. ठीक है. So position of nth dark fringes in Young's double slit experiment is given by all these things. Next. Now, the phenomenon of interference is based on. आता आपण असं म्हटलं की इंटरफिअरन्स म्हणजे काय, light plus light is either maxima of intensity or minima of intensity. Light plus light म्हणजे light waves. Light plus light is either maxima or minima. Okay, maxima or minima. Maxima केव्हा असेल तर पाथ डिफरन्स इक्वल्स टू n लॅम्बडा असेल तर. ओके. आणि मिनिमा केव्हा असेल, लाईट प्लस लाईट इज अदर मिनिमा. हे केव्हा असेल तर डेल्टा इक्वल्स टू n प्लस और मायनस हाफ इंटू लॅम्बडा. ओके, दिस वी हॅव सेड. म्हणजे या ठिकाणी काय होतं तर इंटेन्सिटी सुपरइम्पोज करते, इंटेन्सिटी वाढून येते मॅक्सिमाच्या ठिकाणी आणि मिनिमाच्या ठिकाणी ती ऑलमोस्ट झिरो होते. ठीक आहे. द फिनॉमिना ऑफ इंटरफिअरन्स इज बेस्ड ऑन कॉन्झर्वेशन ऑफ मोमेंटम, क्वांटम नेचर ऑफ लाइट, कॉन्झर्वेशन ऑफ एनर्जी और कॉन्झर्वेशन ऑफ चार्जेस. ओके. आता कॉन्झर्वेशन याचा अर्थ जर तुम्हाला समजून घ्यायचा असेल तर लॉ ऑफ कॉन्झर्वेशन ऑफ एनर्जी आपण म्हणतो. लॉ ऑफ कॉन्झर्वेशन ऑफ एनर्जी, मास अँड एनर्जी असं म्हणतो आपण. बरोबर. लॉ ऑफ कॉन्झर्वेशन ऑफ मास अँड एनर्जी. इथे आपण दिस व्हेरी फेमस इक्वेशन E इक्वल्स टू mc स्क्वेअर, E इक्वल्स टू mc स्क्वेअर. आपण काय म्हणतो की युनिवर्स मधली टोटल एनर्जी आणि टोटल मास हे जे आहे ते कॉन्स्टंट आहे. एनर्जी आपण क्रिएटिंग करू शकत नाही आणि डिस्ट्रॉय पण करू शकत नाही, पण ह्यांचे एक्सचेंज होऊ शकतं. कॉन्झर्वेशन मीन्स एक्सचेंज. एक्सचेंज ऑफ एनर्जी इंटू मास अँड मास हॅज टू बी एक्सचेंज इंटू एनर्जी. दॅट इज कॉल्ड लॉ ऑफ कॉन्झर्वेशन ऑफ एनर्जी. मीन्स इथे मोमेंटम कॉन्झर्व होत आहे का तर नाही. क्वांटम पिच ऑफ लाईट कॉन्झर्व तर नाही. कॉन्झर्वेशन ऑफ एनर्जी, इंटेन्सिटी वाढतीये म्हणजेच काय तर दॅट इंटेन्सिटी इज गोइंग टू कॉन्झर्व into energy. So that is explained. In interference phenomena, energy is distributed such that intensity of resultant wave is maximum at some points and minimum at another points. Therefore, phenomena of interference is based on conservation of energy. Okay, conservation of energy. Next one. Now, remember, we'll discuss this conditions, that is condition for maximum intensity, where superposition of waves takes place, A1 plus A2 square, intensity at the location of minima, where the superposition of two waves takes place, A1 and A2, where A1 and A2 are the amplitude of first wave and second wave, respectively. Here also, amplitudes of first wave and second wave, respectively, to produce maximum of intensity, to produce minimum of intensity. Okay, so what they're asking, two light waves of intensity I1 and I2 having same frequency pass through same medium at a time in same direction and interfere. Okay, then sum of the minima and maximum intensities यांचं काय होईल. ठीक आहे, इथे आपण लक्षात घेऊया I1 आणि I2 ह्या दोन इंटेन्सिटीज आहेत. द सम ऑफ मिनिमा अँड मॅक्सिमा म्हणजे आय मॅक्सिमा प्लस आय मिनिमा इथे आपण ऍड केलंय. ठीक आहे, आय मॅक्सिमा अँड आय मिनिमा यांचं ऍडिशन केलं काय होईल, A1 प्लस A2 ब्रॅकेट स्क्वेअर सबस्टिट्यूट केला 1 2 इथे A1 प्लस A2 रिझल्टंट काय होईल, A1 स्क्वेअर प्लस A2 स्क्वेअर प्लस ट्वाइस A1 A2 प्लस A1 स्क्वेअर प्लस A2 स्क्वेअर मायनस 2 A1 A2. I maxima plus I minima equals to 2 into A1 square plus A2 square. Okay, मायनस आणि हा प्लस हे एकमेकांना कॅन्सल होतात आणि शिल्लक काय राहतं, तर 2 हा A1 स्क्वेअर हा A1 स्क्वेअर 2 A1 स्क्वेअर हा A2 स्क्वेअर हा A2 स्क्वेअर 2 A2 स्क्वेअर 2 is taken common, so we are getting this I max plus I minimum equals to 2 into A1 square plus A2 square, but I is directly proportional to A square, therefore I maximum plus I minimum equals to 2, because I is directly proportional to A square, that is at the superposition. Therefore, I maximum plus I minimum equals to 2 into I1 plus I2. ठीक है? So, what is the meaning of this? I maxima plus I minima equals to 2 into A1 square plus A2 square. So, what is A1? A1 is the intensity of, A1 is the amplitude of wave having intensity I. I is directly proportional to A square. ठीक है? And therefore I maximum plus I minimum equals to 2 into I1 plus I2. So this is the correct answer. I1 plus I2. ठीक है? Because A1 square is to be substituted by I1, A2 square is to be substituted by I2. So the correct option is 2 into I1 plus I2. Okay. Next one. Two identical light waves having phasor difference phi. Hello? Okay, so we'll discuss the remaining points in the next lecture. If time permits, we'll try to cover all the remaining points. You may have the screenshot of remaining problems, those are solved. Okay, and just find out whether the options are correct or anything else. We'll discuss it. If any doubts are there, you can contact me or you just put the message on your students group or to Amdolskar sir. Okay, you can just have the comment and we will interact with ourselves. Okay, thank you very much.